Yeah, so this review, for an elastic collision, we can take the object's mass times its velocity, add to the second object's mass times its velocity, and that total number won't change. For inelastic, we can take the object's mass times its velocity and add it to the second object's mass times its velocity, and then the final product is going to be the total mass times the new velocity. So these are two useful equations for collisions. And if there's a third object, then you would add plus m3 v3 would equal a new constant. And so same thing over here, you add a plus m3 v3 would equal some new velocity times m1 plus m2 plus m3. If there's a fourth one, you just keep adding m's. So just the trend continues. All right. Impulse, as we said, was a change in momentum. So delta p means change in momentum, which if we think about how do we figure out momentum? We took the object's mass times its velocity. Now it would actually be delta m times delta v, but generally objects don't change their mass. They can, but they don't generally. So I'm going to just simplify and just say it's the object's mass times its change in velocity. We can also think about it as how much force is applied to that object times the time that you apply that force. Now, if I apply, let's say I had a semi, and I apply a constant force to that semi in a given amount of time. If I apply a constant force for a long time, I'm going to change that semi's velocity quite a bit. If I apply that force for maybe like 10 hours, the velocity of that semi is going to get pretty high. So if I apply more force, the velocity will also go up more. So you can change an object's momentum by either applying more force or apply that force for a longer amount of time. And this would be a net force. I guess it's not really applied force, a net force. A net force times delta t equals your change in momentum, your impulse. What are some applications of impulse equations? Well, you think about it, I'll come back to that. Impulse, we can figure out if your impulse is constant, which oftentimes it is, if you change the amount of time on something, like let's say you had the egg drop is a famous experiment. The egg drop, if you drop an egg from a 2-story high building, the egg will break. But there's ways around that. If you slow the egg down, when maybe it lands into water, well, it might not break then. It might not. But it's going to stand a better chance because there's going to be a longer amount of time for that force to be applied, which means the impulse is going to be less. So what are some applications of impulse then? Well, airbags. You think about an airbag. What does an airbag do? Well, it's a collision when in the collision you collide with the airbag. Bam. All right, and you think about there's a lot of force there, but imagine how much force it would be if there wasn't an airbag. Impulse stays the same, and since the airbag absorbs some of that time, meaning when you go into the airbag versus like the windshield or the dashboard, there's a lot more time that you're able to slow down, which means the force is less because impulse is the same. Your change in momentum is still the same, but it's over a longer period of time. Crumple zone in cars. Cars are designed so that the different parts of the car will crumple, meaning that they absorb a lot of that impact. Well, how does that help you? Well, if the cars were indestructible, when they collided, you would that time for the impulse would be very small. There'd be a lot of force on the car and your joints and your bones and your body. Seatbelts, another example. Seatbelts slow you down so it's less force. Counter examples to this, like where would you want more force? Well, what about golf club golf ball collision? You want to have as little time as possible in that collision so you get a lot of force. Baseball bat and a baseball. You want a little bit of time. The smaller contact time you have between those two objects, the larger the force. You want a large force with a golf ball and a baseball because you want to go far. So if you think about it, if F times delta T is constant in a collision, if one changes, the other one changes inversely. Means if F goes up, delta T must go down. The change in time must go down if the force goes up, or vice versa. That's what that means. So let's review. Let's think back to the lesson again. So, do you know how to define momentum? What is momentum? Can you define what impulse is? What is impulse? Can you determine the difference between an elastic collision and inelastic collisions? This should say inelastic collision. Can you use momentum and impulse equations to calculate velocities, masses, and forces? Well, momentum is, go back to the first slide, that. Impulse is that. The elastic collision was where there's no loss of kinetic energy. They basically bounce off each other. Inelastic, where they stick together, there is some sort of loss of kinetic energy. And these are equations for momentum. This is the equation for impulse. So there it is. So that's that, and hopefully you had a good time. Have a great